Okay, so let's work this problem. We've just started talking about conjugate beam, so we'll use that for our solution. Right now it just says determine the slope and displacement at point B. So there's a couple ways that we could do it. We could use direct integration like we talked about before. You'd have to write a moment expression that's good over the first 6 feet and a second moment expression that's good over the next 6 feet. Connect them here where they have a common point, solve for all the integration constants, and then just evaluate it at B. That can be done. What makes conjugate beam very powerful for this problem is you don't want an equation for the displacement and the slope. You want the slope and displacement at a point, right here at B. So I don't really care about what it is anywhere else. I just want it at one particular point. So what conjugate beam will allow us to do is solve this problem and find, if you remember conjugate beam, in the conjugate beam, shear and moment is slope and displacement in the real beam, so we just have to find shear and moment at the conjugate beam at B. Yeah.
I think in the homework problem it wanted the angle at the middle where the 15 kip was.
Oh, we can find that too.
Gotcha.
Is that the one that it wants in that problem? Hang on a second, let me flip back. So the particular it wants to determine the slope at, there B is in the middle. Okay, so B, and what else did it want? Maximum displacement. So maximum displacement will occur at the free end. So let me do this. We will find the slope at the middle and the displacement at the free end. So I'll make a little adjustment for that. So what's the first thing we have to do in all these problems once you decide for conjugate beam? Got to draw the moment diagram, right? So first thing we need to find is the shear at A and the moment at A. So you have to do a little statics first. So I'll come over here and we'll sum moments at A, make sure we're in equilibrium. And what do we have? We have the reaction moment, which is actually negative, using right-hand rule. And then I have this 15 kip force creating negative moment with the moment arm of 6 feet. So it looks like my moment at A is actually a negative, is that 90? Does that sound familiar? Did you guys do that for homework?
Yeah.
Okay, and then we'll sum forces in the y direction. This is a pretty easy equation to solve. So I have my shear at A acting up, and then this 15 kips acting down. So the shear at A is 15. So with that information, I can quickly draw my shear force and bending moment diagram. So I'll have a little template here where I can establish positive X, positive shear, and we'll draw the shear diagram. So our shear starts off at a value of 15, and it's positive. There is no load, so there's no change in shear, so it stays 15. And since the value of the load is 0, the slope is 0. And then you can see it matches this value, so our shear diagram is just this kind of step function. Any questions about that? So now our moment diagram, positive X, positive moment. Our bending moment starts off at negative 90. And remember, the change in moment is the area of the shear diagram, and the area of the shear diagram is positive 90, so it brings us to 0. Also, the slope of the moment diagram is given by the shear, and the shear is constant and positive, so I have a constant positive slope. So there's my moment diagram. I think you'd be pretty happy if you got this problem for the exam for a shear moment diagram.
What's the likelihood that this will be a shear?
What's the likelihood of that? I would say it's about the same as winning the lottery.
So you're saying there's a chance?
There's a chance. Slim, but there's a chance. Somebody always wins, right? Somebody. Okay, so what we need to do first is I need to now draw my conjugate beam. Now, if you remember from our discussion previously, we now have to look at the supports and look at their conjugate supports. So, a fixed connection in a real beam maps to what in the conjugate beam? A free end. And the free end becomes fixed. So really what happens is the beam looks like it just kind of turns around. Now remember, that's not a pattern that you should seek to find every time. So we just map the conditions. Now, we apply the conjugate beam M divided by EI as load. Alright? So you'll notice our moment here is all negative. So what's a negative load? Up or down? It's down, right? Now what I like to do sometimes to help you kind of not miss it is I like to just take the moment diagram and just put it on the beam. So you don't have to think about anything. There it is. I just took the moment diagram, put it on the beam. Now, because this is negative moment, I know my forces are down. And I also know my value would be 90, and that's kip feet, because it's a moment, divided by EI.
So
okay? Go ahead.
How do you determine the reactions in the conjugate beam?
Just statics. So really all we've done now is we've taken our real problem and we've converted it into a conjugate beam problem. And at this point, we're working this problem. So just forget about all that other stuff. So if I were to give you this problem, this is still 6 feet, and this is still 6 feet. All right? Now, I didn't list it here, but one of the answers that you need is the displacement, the maximum displacement of the beam. Right? And that will occur at the free end, which in the conjugate beam is now fixed. So if I find the moment at this fixed connection, that will give me the bending moment. And the bending moment in the conjugate beam maps back to what in the real beam? Displacement. So the first thing I need to do is find the bending moment at that fixed connection. So first thing I'll do is I'll get the concentrated equivalent force for this. It's a triangle, so it should be 1/2 base times height, which is 270. So I get 270, and that's going to be kip feet squared divided by EI. Now I'm going to sum moments about this end here, so I want this distance. What is that distance? Well, I know this much of it is 6 feet. And what's this part? Well, it's 2/3 of the base, which will be what? 4. So it'll give me a total moment arm of 10 feet. So now I can come in this space and I'll just simply sum the moments at, I called it B here, but to match your other problem, I think this is C and this is B. So I'm going to sum moments at C. Yeah.
Can you repeat what the distance thing?
I'm sorry, Mr. Pong, what did you say?
The distance at the top of the...
Oh, the distance to the centroid here?
Right. Oh, okay.
That's what this is. So the first 6 feet just gets us to the middle, and then I know that the centroid of a triangle is 2/3 the base distance. So 2/3 of 6 is 4. So I have to add all those together. Oh, also I forgot to include that I do have a reaction moment at C, and that's positive bending moment. So with that said, I just do my statics. So The moment at C is positive. About C, this force creates a positive moment. Let's see if I can squeeze this in here. 270 kip feet squared over EI times 10 feet. Sorry. So it looks like the moment at C is negative 2,700 kip feet cubed over EI. Negative displacement means that the point at C moves what? Up or down? Down. And that's reasonable. I would think that C would move down under this loading scenario. Now, the actual problem in mastering engineering says that we need to determine the maximum displacement of the beam measured upwards. I guess that means upwards is positive. So now you would have to put in your values of E and I here to actually get a numerical value. So really now the displacement at C is going to be equal to that. So I'll have 2,700 kip feet cubed divided by EI, and then I'll have to do some conversion. So I'll make a little line here. Now the values that I was given was 29,000 KSI. And that's kips per square inch. And then I got a value for I of 660 inches to the fourth. And now I need to do a conversion. And I know that there's 12 cubed, or 1,728 inches cubed in a foot cubed. I think if you look at this carefully, you'll see the kips cancel, the feet cubed cancel, and I have inches to the fifth divided by inches to the fourth, which should just give me inches. And give me a second to make that calculation. I got 0.244. Does that sound? Well, you guys got different values, didn't you? I guess the proof will be, you won't be able to see it in this video, but I'll go over here and I'll enter that into my value here, 0.22. You said use 3 significant figures. And I submit it, and I didn't get it right. Did I forget units? Does it need to get units? What did I do wrong? If positive value is displacement is upward, negative value is down. So I put negative in. You need units in this problem? How do you enter units?
They should be there. Yeah, sure.
You should already have these.
They didn't do
Look to
anything.
the far right.
Look on the far. Oh, I see it now. Yeah. Somehow I missed the problem. Maybe I calculated it incorrectly. Let's try it again. 2,700. Anybody else try this?
Yeah, I calculated that.
You got the same number? Yeah, I got 0.244. It said 3.
Unless there's different values for like that.
Oh, I entered it wrong. It's 0.244. I entered 224. Well, now I got it right. Okay, so that's the correct answer. I just fat fingered it when I put it in.
The value that the mastering engineering gave us for
Yeah. So just to make sure I got it right, I'm not using these values. These are the values that I was given in mastering engineering, and you may have gotten a slightly different number. You guys remember did anybody get something different? You remember?
I got 620 for the.
Okay, so yours will be off just a little bit. But the concept is the same. Now the second part of the problem wants to know what's the slope at B. which is here in the middle. So slope in the real beam matches to what in the conjugate beam? Shear. So I need to find the shear here. So what I would do is cut the beam at C, and now you have to decide whether you want to look at the left side or the right side. Now, I'm going to go with the left side because I've already done all the work for the left side. If I wanted to use the right side, I'd have to find the reaction force. Would be hard to do, but I'd still have to do it. So for the slope, I'm going to cut the structure and look at the right-hand side. I still have my force applied, or my M over EI. So this is still 90 kip feet divided by EI. This is still 6 feet. What else do I need to know? Oh, I need to know the shear at B. Now there would be a moment there too, but I'm not interested in that. But if I did find the moment at B, what would that tell me? That would tell me the displacement at B in the real beam. The problem that I'm interested in only wants the displacement at B, so I just need that value. We've also found too that the concentrated equivalent of that distributed load is 270 kip feet squared, again divided by EI. So you can see our equilibrium is going to be pretty simple. If I sum forces in the y direction, and I'll assume up is positive. Let's make sure everything's in equilibrium. I've got this 270 kip feet squared over EI acting down, and I have my shear at B also acting down. So it looks like my shear at B is negative 270 kip feet squared over EI. So should my slope at B be negative? I think so. I think your deflection is going to look something like that. So you can see we have a negative displacement, and you can look at the slope here, and that's a negative slope. So the signs seem to match. So to actually calculate a value, so my displacement at B in the real beam will be that 270 kip feet squared, and now we'll divide it by E, which my E value is 29,000 kips per inch squared, and my I value was 660 inches to the fourth. But now I have feet squared, so there are 144 or 12 squared inches squared in a foot squared. So again, kips cancel, feet squared cancel, and you can see I have inches to the fourth in the numerator, inches to the fourth in the denominator, so I get a dimensionless value. Let's see what that's going to be. Usually these are very small. I got 0.002, and that should be radians. Oh, I forgot my minus sign. There it is. So let me just give me a second to come back over here and enter that in. How many significant figures? Oh, he wants 3 significant figures. Hang on a second. I don't have that for such a small number. Somebody else calculate that for me. What's 3 significant figures? I got 0.0020, but that's when my display stops. Anybody else know how to? 203. And I'll submit that. And hey, we got it right. Yeah. That'd be good enough for me. That's a very doable problem for the exam. I mean, we've been chatting about it and doing other things, and it's only been about 19 minutes. So I think that's a very doable problem. Any questions about that one before I stop it? All right.